Welcome to the Organic Chemistry Podcast, Dr. Brian Lloyd's Scribblecast of Organic Chemistry Lectures and Solutions to Homework Problems. In this Scribblecast lecture, we're continuing our investigation of the derivatives of carboxylic acids, and we're looking at esters, continuing with a look at the reactions that esters undergo, so reactions part 2 if you like. In the last Scribblecast lecture, we looked at the reaction with water to produce carboxylic acid, examined how it went under nucleophilic acyl substitution as opposed to the SN2. We did find one example of a molecule that underwent the SN2, which was methyl 2,4,6-triterbutyl benzoate. And then we looked at the alcoholysis reaction. Reactions with alcohol produce esters. And you can use a different alcohol than leaving group to carry out what is called transesterification. Now both hydrolysis reactions and alcoholysis reactions can take place in acid or in base. What we're going to do next is examine a reaction with ammonia. Okay, so reactions with ammonia. Need blue. Ammonia. Or primary or secondary amines. If we take an ester such as methyl benzoate, and we treat this with ammonia, we can produce an unsubstituted amide. Plus methanol. And so we make the molecule benzamide. Benzamide is an unsubstituted amide. That is, there's no substituents on the nitrogen. If, however, I use an amine, and this time let's use a secondary amine. We've been using primary amines a lot. So let's use dimethyl. So here's a CH3 twice NH. If I use dimethylamine, I will produce an amide. Off of the nitrogen, there are 2 methyl groups. And again, of course, in this case, we're kicking out methanol. So there you have it. We've produced a benzamide again, but it has 2 substituents off the end. So we've got N, dimethyl, benzamide. Okay, and then dimethylbenzamide. Now, this reaction again undergoes nucleophilic acyl substitution. I'm going to just draw it, the phenyl group, represent that by an R. We have a C double bond O CH3. And we attack this with ammonia. Ammonia is a very good nucleophile, has a lone pair, attacks the carbonyl, and we get our CO minus, NH3 plus, oops, I forgot my oxygen again. Do that a lot. OCH3. Lone pair of electrons comes back in to build the pi bond. We kick out the alkoxide. We get R, C double bond O, NH3 positive. Protonated amide is very acidic. And we get a very powerful base, methoxide. So it's not surprising that the alkoxide grabs the proton very quickly. And we end up with the unsubstituted amide NH2 and methanol. And this mechanism is much the same as we've seen in all of the mechanisms so far in the hydrolysis and alcoholysis reactions of esters, the transesterification reaction. Nucleophilic acyl substitution is the predominant reaction pathway. The next reaction we want to look at is the reduction of esters. Reduction. Now, the reduction reaction of esters can proceed by two different paths. There is catalytic hydrogenation the reagent of catalytic hydrogenation is H2 gas with a catalyst. Okay? The catalyst can be either nickel or palladium or platinum. And often heat may be involved. There are examples of other types of catalysts that have been used. Other catalysts are copper, Cr2O4. Okay. That's also been used as a catalyst. The other methodology is metal hydride reduction. And in this case, you've got to use a powerful metal hydride. And so the metal hydride that's used as the reagent most often is lithium aluminum hydride. And we're going to look at the reactions, both of these reactions. So let's begin with catalytic hydrogenation. I can take a molecule of methyl benzoate and react it. And so I could use, for example, H2 gas in the presence of platinum. Or I could use H2 gas in the presence of copper, Cr2O4. If I do this reduction, the reduction process leads to elimination of the alkoxide as methanol and reduction of the carbonyl to an alcohol. So it produces two alcohols, benzoyl alcohol plus methanol. Reduction with metal hydrides can also lead to the same products. If I use lithium aluminum hydride, which is often reacted in ether, in step 1, and then add H2O or acid, I can destroy the aluminum. Aluminum hydride essentially puts H- on. You eliminate the alkoxide, producing aldehyde. Further reduction will lead to benzoyl alcohol. Let's take a look at the mechanism, or proposed mechanism, for the metal hydride reduction. Let's use R, C double bond O, OCH3. And let's have an H, aluminum H3 coming in. It's negatively charged. Hydrogen's more electronegative, so it's a delta minus on the hydrogen, delta plus on the aluminum. The aluminum is certainly going to be attracted to the lone pairs on oxygens, but initially the delta minus is going to be attracted of the hydrogen to the delta plus on the carbonyl carbon. And so the electrons move to the hydrogen and the hydride goes on here. Initially what we form then is an RCO minus, the H, and the OCH3. Now this very quickly, the O minus is probably interacting with the AlH3 Lewis acid that has formed from my aluminum hydride. That is, the aluminum's probably binding to that. But the pi electrons restore the carbonyl. Essentially what's going to happen is you're going to have the CH3O minus leave. And CH3O minus will associate with the lithium, very quickly displace that and be associated with the aluminum. The aluminum H3 that formed. And what we'll have then is our C double bond O H. And of course the whole process can happen again. Another H aluminum H3 come in, delta minus, delta plus, and the H go for the carbon. And what we end up with, of course, is R, C, O minus, H. We've added a second H. This interacts, of course, with the aluminum hydride that has the empty orbital. Finally, once we're done, we throw in water or acid and we protonate the alcohols. We'll protonate this and the methoxide and we'll end up producing our RCH2OH plus the methanol. All right. Now, reduction reactions via alkylation with Grignard reagents are common reactions of esters, reactions that we looked at in the free radical section of alkyl halides, since Grignards can be prepared from alkyl halides. And we learned, for example, in Grignard reagents that formate esters esters of methanoate gave us secondary alcohols. That is, I can take methanoate, methyl methanoate, for example, and I can react this with methyl magnesium bromide or ethyl magnesium bromide. Let's use ethyl. Like the hydride case, carbon is more electronegative than magnesium, so there's a delta minus. This acts essentially as a C minus and will attack here. When it does so, you'll get HCO minus, OCH3, and in this case we have an ethyl now on here. Of course, we can reform the pi bond, kick out methoxide, and we'll have H, C double bond O, CH2, CH3, plus OCH3 minus, which will associate with the magnesium. Magnesium's positive. Now, so we form a salt. The problem with this is we can't stop the reaction. The aldehyde will be subject to attack by methyl. Sorry, we're using ethyl. Magnesium bromide. And another one will attack, and it will go for the carbonyl. And so what we end up with is HCO minus. We've got one CH2 CH3 on. We have the second CH2 CH3 on. So essentially two ethyl minuses add onto the ester. We can't stop the reaction at the aldehyde. It's very difficult to isolate good yields of the aldehyde. Not the best way to stop the reaction. And so in our last step we throw in acid, separate from the Grignard, so it's step 2. And we end up producing our alcohol, CH3, CH2, CH, CH2, CH3, OH. Only this part of the molecule came from the ester. The two ethyls came from the Grignard. So there's the full-blown reaction. Alright? So we can draw it in one step if you like. If we draw a reaction, draw a big reaction arrow. 1 ethyl magnesium bromide, 2 H3O plus is the overall. Now we can repeat this reaction for any other ester where in place of H we have some other substituent. If, for example, I had a CH3 here, this would have been a CH3 all the way through. If that was a CH3 all the way through, this H would have been a CH3, and I'd have a tertiary alcohol. So all other esters yield tertiary alcohols for this type of reaction. So formate esters give you secondary alcohols, and all other esters will give you tertiary alcohols. Okay. Now we want to revisit a form of chemistry that we really haven't examined since carbohydrates. It was important to carbohydrate chemistry, and so it's important to look at it. And that is an ester group found in a ring. Probably should have covered this in the preparation of esters. But these esters are cyclic esters. And cyclic esters Cyclic esters are called lactones. Lactones. Now, a molecule that possesses a carboxylic acid functional group at one end and a hydroxyl group that's 4 or 5 carbons away can undergo intramolecular esterification very easily. For example, if I have HO, CH2, and then 2 CH2s, and then a C double bond OOH. 4-hydroxybutanoic acid. And suppose I take 4-hydroxybutanoic acid, which, by the way, a common name is a carboxylic acid. Here's the alpha carbon, the beta carbon, the gamma carbon. So this is gamma hydroxy butyric acid. And if I react this under acid catalysis, just like an ester, the alcohol end can wrap around and attack, and I can produce, if this wraps around, an ester group. Now, what's interesting is IUPAC nomenclature for this type of molecule is based on butanoic acid, but instead of dropping ic acid, instead of adding 8, I add lactone, butanolactone. And I cut to count 1, 2, 3, 4. It's at carbon 4 that the oxygen cyclizes, so this is butanol 4-lactone. Sometimes you also can name it in common nomenclature, drop the ic acid and add O-lactone. So this could be called gamma hydroxy. And what it's telling you is when you say butyrolactone, is that that hydroxy group is wrapped around to make the ester. Now, a 5-membered ring is really optimal when there's one sp squared carbon involved. That sp squared carbon certainly makes the 5-membered ring one of the favored structures. We explained why this was so prevalent in gamma lactone. Chemistry and carbohydrates. And let's try another one. If I try 5-hydroxypentanoic acid, that is, I add one more CH2, I can react it in acid, and I will produce a 6-membered ring. What is called pentano 5-lactone. or based on the common name, alpha, beta, gamma, delta. This is a delta hydroxy valeric acid. So let's write their names down. 5-hydroxy pentanoic acid becomes a pentano 5-lactone, or delta hydroxy, eat up, boy. Okay, there you go. Delta hydroxy valeric acid. So pentano 5-lactone has the common name delta hydroxy valerolactone. There you go. Right. Now, the reaction is acid catalyzed, but the optimal ring sizes in both reactions, due to low ring strain, allow the reaction to proceed even in trace amounts of acid. The reaction mechanism is a standard nucleophilic acyl substitution. All right? We can draw that mechanism here. And we can draw it for the 6-membered ring. So here's 5-hydroxy pentanoic acid. And we have lone pairs. And in acid, we can protonate. Increasing the polarity of the OH bond here. When that happens, oops, this guy can attack, pi electrons move out. Once that happens, we have OH, lone pair and a positive charge on oxygen attached to the C, which now has 2 OHs attached to it. Minus H plus will generate our cyclic ring structure. Plus H plus will protonate one of the OHs, making a good leaving group. I'll just put OH2 plus. Water's a better leaving group. Once that leaves, minus H2O, we have O, Smooth it over, give me some room. Draw it up here. OH plus carbocation. That carbocation is resonance stabilized. Can have the pi bond to the oxygen in the ring. If you do that, you get a plus here. Or you likewise can have the double bond to the OH, where it dumps in its lone pairs. And clearly this one's set up to deprotonate. Minus H plus will give us the lactone. So going backwards is just plus H plus H2O, minus H plus H plus, minus H plus here. So it is a reversible equilibrium. And the final product, pentano 5-lactone, is a delta lactone. Now, as ring strain increases, the probability of this OH wrapping around and properly hitting the carbonyl, producing a chain of events that generates the lactone, decreases. By the time we get to longer chains that would produce very large rings, there's a tendency to polymerize. For example, if I take 7-hydroxyheptanoic acid, so we have 7 carbons. One, two, three, 4, 5, 6, 7. Seven hydroxyheptanoic acid. When you hit this molecule with acid, it tends to polymerize. That is, this OH is not in proper proximity to wrap around and strike the CO2H, so you don't form a ring structure, but rather it will attack another molecule. And so you get repeating chains. You produce a polyester of O, CH2, bracket CH2 5 times, C double bond O, and that attaches to another. Now polyesters, where it just links up and keeps repeating and you get X numbers of these repeating, can link up and create a polymeric chain. What do you have to do to get the OH to wrap around? Produce what is essentially heptano 7-lactone. With 7 carbons, add the oxygen in, you're going to have an 8-carbon ring, or 8-atom ring. 7 carbons, 1 oxygen. This would be heptano 7-lactone. Now, how are you going to produce heptano 7-lactone from 7-hydroxyheptanoic acid? The only way to do that is stop or slow down this polymerization. How can you slow down this polymerization? Well, to form the polymer, one molecule of heptanoic acid must crash into another molecule of 7-hydroxyheptanoic acid. If you lower the probability of that collision by diluting the solution, you increase the chance more time for the molecule to wrap around and hit itself. Although it is rare, it still can happen. This is a more strained ring, and you can form molecules that are less favorable. So what we have to do to make heptanyl lactone is use a very dilute solution. So there's no chance of polymerization. So a dilute solution. Lastly, with regards to lactone chemistry and carbohydrates, we can't forget about this molecule. The ester version of L-ascorbic acid. L-ascorbic acid is simply vitamin C, which is a very important gamma lactone. Okay. Well, having mentioned that we can polymerize and make polyester molecules, perhaps the next thing we should look at, very important branch of organic chemistry industrially, is polyester chemistry. The reactions that produce polyesters. Polyesters represent about half of the synthetic fibers produced industrially. That's impressive. Think of all the polymers out there used in everything from clothing to carpeting to plastics. About half of the synthetic polymers made industrially, the synthetic fibers that are produced industrially, are polyesters. One very important form is polyethylene terephthalate. Let's write that down. Polyethylene terephthalate. For short, it's called PET. P-E-T. PET. Comes from the P, E, and the T. Now, when produced in a fibrous form, this polymer, as a fiber, is called dacron. Dacron's used in clothing and as tubes to replace blood vessels in the human body. In fact, human tissue can grow in and around dacron, allowing it to be incorporated into the body's structure. When it's produced in film, in a flat film, the film is called mylar. Mylar film. Mylar film has been used in magnetic tapes and CDs. Polyethylene terephthalate, or PET, can be synthesized by taking 1,4-benzene dicarboxylic acid. Let's see that. 1,4-benzene dicarboxylic acid The common name of this dicarboxylic acid is terephthalic. Hence you see where the name terephthalate comes from. So this is 1,4-benzene dicarboxylic acid. It's also called terephthalic. Okay, so I take this, I react it with methanol, and I produce an ester in acid. Methanol will produce dimethyl 1,4-benzene dicarboxylate or dimethyl terephthalate. In other words, produce this. Clearly this is simply an ester. It's not a polyester, it's just a standard ester. What we do now is react this with an alcohol, which will allow it to polymerize. It's actually a diol, ethylene glycol, or 1,2-ethane diol. We throw it in acid, okay, and we do the reaction at quite high temperature, 150 degrees, to help remove the water, drive the reaction. And we make sure we have two equivalents of this. And so ethylene glycol will go on in transesterification and we'll get an O on one end. And we can get an O on the other end. And then the free OH can attach to another. And you can see what's going to immediately happen. We're going to get O, C double bond O, C double bond O, O. We're going to have our CH2, CH2, and it's going to attach to another. Terephthalate, and this is going to continue. We'll get a repeating chain of this, alternating between terephthalate, ethylene glycol, terephthalate, and so on. The N value here, N typically equals 80 to 130 units. If it's a fiber, it's Dacron. And if it's a film, it's Mylar. This is one example of a polyester and the strategy involved in making polymeric fibrous materials, film-like materials that can be used. But ester chemistry does extend beyond the carbon-oxygen double bond. The standard ester structural framework is an R, C double bond O, O, R prime. It is possible to make analogs of esters by using carbonyls where in place of the OR prime we have an SR prime. Such a molecule is referred to as a thioester. Now, one very important use of thioesters occurs in the biochemical transfer of an acyl group between molecules in the cell. In cells, thioesters function as acyl transfer reagents. They basically move groups like this around. Maybe I'll use an R. R, C double bond O. This type of functional group is handled, the movement of this functional group is handled by thioesters. Key to the transfer is a molecule called acetyl coenzyme A. It's a very large molecule and you're not going to have to draw it, although I have provided it to you in your notes. We've got the time. Why don't I just take a moment and sketch it out? If you're curious, you can watch. If not, you can fast forward and jump this section. What does acetyl coenzyme A look like? Well, the coenzyme, the alcohol, the SR prime, the coenzyme A is a very large molecule. We have an HS, CH2, CH2, and then we have an NH, C double bond O, CH2, CH2, NH, C double bond O. Now we have a CHOH, carbon with two methyls off of it, CH2, and some phosphate groups, O, P, O, OH, double bond O, P, OH, double bond O, OCH2, we have the C, and we have what looks like a furanose type ring. And this connects up into this base unit. Quite a large molecule. You may have to learn it in your biology courses. I'm not going to require you to know this at this time. I have to make room for the NH2 off of here. We have an N here, and an N here. And there we go. This is coenzyme A. This is the R prime group on the S, and there's the SH. Acetyl coenzyme A, therefore, is often written as a CH3 and an S, and you often write it as COA, where CoA represents all of this unit. The importance of acetyl coenzyme A can be seen in its reaction with the molecule choline. If I take choline, so let's write the coenzyme A over here, the acetyl coenzyme A. And I react this with choline. We've talked about choline and phospholipid chemistry. If we react this, we can make the ester. So we do this reaction, and what can happen is we can put an acyl group on the OH end. If we do, we get this molecule. This is a very important molecule called acetylcholine. Acetylcholine. Acetylcholine is a very important biochemical, a neurotransmitter, and it can be synthesized for acetyl coenzyme A. So, thioester chemistry is very important biologically, and you should know this reaction as an example of that importance. So there you have it, the chemistry of esters and thioesters. We finished off the ester functional group. We're going to press on with the next carboxylic acid derivative, next Scribblecast lecture, and that is amines. I'm Dr. Brian Lloyd. This is my Scribblecast. I thank you for listening.